recently read this manifesto from former NASA Administrator nominee Jared Isaacman. In the heart of his argument, he said this, quote, "Ultimately, we should move beyond space launch system. The agency should redirect talent and resources to nuclear electric propulsion." And this was proposed for a reusable system to get human landings on Mars. Now, this is my first time hearing this argument, and so I decided to look into it. And today we will do a full deep dive of this idea and what it will really take to get human landings on Mars. Starting with some definitions, nuclear electric propulsion is just electric propulsion, but instead of using solar power, which is sort of the standard, we use nuclear power. This is distinct from nuclear thermal propulsion, which uses a nuclear reactor instead of a reaction chamber to heat the propellant. Electric propulsion uses electric and magnetic fields to accelerate charged particles of propellant. An example of this is the argon Hall effect thrusters used on Starlink satellites to keep them in orbit. These thrusters are much more efficient than chemical rockets, but they also have a much lower thrust-to-weight ratio. This makes them great for maneuvering in space, but not powerful enough to use during launch. So for comparison of a chemical rocket, the SpaceX Merlin engine used on the Falcon 9 has a thrust-to-weight ratio of over 200, and its specific impulse is 350 seconds. And this means that 1 kilogram of propellant can generate 9.8 newtons of thrust for 350 seconds. And so this is a measure of efficiency. A Hall effect thruster, on the other hand, has a very tiny thrust-to-weight ratio, but it'll have a specific impulse of 3,000 seconds or even higher, depending on the type of propellant that you use. So, as long as you're okay with continuous very low thrust and you have enough electricity, then electric propulsion can give you 10 times the acceleration for the same amount of propellant compared to a chemical rocket. This is what makes them attractive for deep space missions like going to Mars, where you will have plenty of time for that low thrust to have an effect. Now, I'll also put on the chart the NERVA engine, which was tested in the 1960s, and this is a nuclear thermal engine. So you can see it is sort of the awkward middle child between these two types of engines, and that's because the thrust-to-weight ratio is still very low, and it's low enough that it's not going to be usable during launch. However, the specific impulse is also much lower than in electric propulsion. Now, these engines are also very expensive and complex, and they require highly enriched uranium, and so this is why these ended up not being fully developed and used in flight. So for electric propulsion, the source of the electricity doesn't really matter, and the only thing that does matter is the mass and the cost of whatever is producing the electricity. And we can describe this with the power to mass ratio, called the specific power, and then the power to cost ratio. For standard high-end solar panels on Earth or in orbit, the specific power is around 40 watts per kilogram. There have been some experiments of solar panels that get over 1,000 watts per kilogram, but the best flight-proven architecture gets 140 watts per kilogram in an extendable solar array. So for our future fully scaled up solar array that we'll use in our calculations, I'm going to assume 100 watts per kilogram, including all of the associated electronics. This specific power will be for the vicinity of Earth, but as we move further away from the sun, the power generated from solar will decrease with the square of the distance. So by the time we get out to Jupiter, a solar panel will be mostly useless. For nuclear power, it's not going to depend on the distance from the sun, so the specific power will be the same at any distance. However, the current designs will not have as high a specific power as modern solar panels. The 1 kilowatt prototype that NASA has fully tested on Earth achieves 2.5 watts per kilogram, so this will only be higher performing than solar panels beyond the orbit of Jupiter. Now, as we scale up the size of the reactor, the specific power is expected to increase significantly. This paper estimates that for a 100 kilowatt reactor, so 100 times the size of what's been tested, the specific power would be 33 watts per kilogram. Also, with all the extra development and safety costs, we should always expect nuclear power to be somewhat more expensive than solar, just like it is here on Earth. So, since this mission that we're planning will be between Earth and Mars, even a better optimized, scaled-up nuclear reactor will still not be as performant as solar. This technology will still be useful for deep space missions. However, for getting to Mars, the competition is really between solar electric propulsion, nuclear thermal propulsion, and chemical propulsion. So now let's compare these options in detail. The most efficient way to get from Earth to Mars with chemical propulsion is with something similar to a Hohmann transfer. So this will take 9.4 kilometers per second of delta V just to get into low Earth orbit, and then you'll need to use 3.6 kilometers per second of delta V to get into the Mars injection orbit. This will take 8.5 months with the most efficient route, but you can shorten the time if you're willing to waste some acceleration. Now, for this mission plan, you can skip the second burn that you would usually need for a Hohmann transfer because you can slow down using the atmosphere of Mars if you have a very large heat shield. Now, for the Martian rovers, they had a system of heat shields and parachutes where they did not need to use a significant amount of delta V for the landing burn. And so for these entire missions, they worked out to around 13.7 or 13.6 kilometers per second of delta V total. For something like Starship, where you need to do a significant landing burn that might be 1 to 2 kilometers per second, the total delta V might be something like 15 kilometers per second. So doing an injection burn and then aerobraking like this is a very, very efficient way to get to Mars. But when you have an electric thruster, you're not able to create this sort of trajectory, and you need to actually use a continuous spiral orbit to get into the orbit of Mars. The spiral burn should also take at least 8 months, and it will actually take even longer to get from low Earth orbit into Earth escape. So to get into low Earth orbit, we will still need to use 9.4 kilometers per second of delta V. Then to get out of Earth orbit into Earth escape, this will take 7.6 kilometers per second, which is roughly the orbital speed that you rotate around Earth at in Leo. And then it will take another 5.65 kilometers per second to go from the vicinity of Earth's orbit into a roughly circular Martian orbit. So we will also assume that we're not going to do any aerobraking in the Martian atmosphere or landing, since this will be a reusable system. And so one way from Earth to Mars, this will be 13 kilometers per second out of Leo, and then also 9.4 kilometers per second just to get into space. And so this will be a total of 22.4 kilometers per second of delta V one way. To make a round trip from Mars back to Leo, this will add another 13 kilometers per second of delta V and take, a year or 2 years at minimum. So that would be 26 kilometers per second from the electric propulsion platform, and then an additional 9.4 kilometers per second to get the platform into space. And so for the reusable mission, this would be a total of 34.4 kilometers per second compared to around 15 kilometers per second for that one-way mission. When you hear that 26 kilometers per second number, that is basically the red flag of this plan, although you'll see that it is just barely possible with the highest end ion thrusters. So when you plug in 26 kilometers per second and 2,500 seconds for specific impulse into the rocket equation, you get around 65% for your mass fraction. So this means on that electric platform, 65% of its mass will need to be that propellant that is usually a noble gas. Now here you can see that for this mission, if you use the chemical or nuclear thermal specific impulse of 350 or 825, this is not plausible at all. However, if you use an ISP of 5,000, then the mass fraction can get as low as 41%. So our problem here is that we still need to account of the mass of all of the solar panels that we'll need for power, and then all of the tanks and structures and the bus of the spacecraft and everything else. And so let's try to design a mission that could work in theory. Choosing which electric thruster to use is a pretty complicated optimization problem where we have these 4 different factors of efficiency. The first is kilowatts per Newton, and this will decide the mass of solar panels that we need. Next is kilograms per Newton of the thrusters. So that means how much mass will our thrusters take up. Then we have the cost, or the dollars per Newton, which means how expensive will all of our thrusters be. And then finally, we have the specific impulse, and this will influence how much mass we need to dedicate to our propellant. And a sort of ideal choice that I found online is this Next C thruster made by NASA and Aerojet. And this is a xenon thruster, and it outperforms the SpaceX Starlink Hall thrusters in most of those categories that I just explained. Okay, now walking through the math, we have the specifications for the Next C thruster. So first of all, we have 29.2 kilowatts per Newton, and this means we will need 290 kilograms of solar panels per Newton of thrust. Okay, we also have 200 kilograms per Newton for the thruster itself. That's self-explanatory. 20 million per Newton because each of these cost 10 million. Of course, that would improve over time, but still. And then we have 4,190 for specific impulse, which is most important. Okay, so for our electric propulsion design, we're assuming the entire thing will weigh 2,000 tons in total, and it will have a payload of 500 tons. And this is actually pretty small if you think about it, because a fully loaded Starship would weigh over 1,500 tons. So we take the full 26 kilometers delta V for our mission, and we assume that it'll last 4 years, and we have this acceleration that we need. Okay, now we roughly approximate that when we burn half of our fuel, we have 1,470 tons. So our average force will be around 294 newtons. So this much thrust will require almost 9 megawatts of solar power and 1,290 of these next C thrusters. This works out to 144 tons of solar and thrusters, and then 940 tons of xenon propellant. And this means we would have our 500-ton payload, and then we'd have 416 tons left over for all of the tanks and everything else. So you can see when we're using the ideal thruster, and also pretty much ideal solar panels and everything else, you can see this kind of barely theoretically works. Okay, but in practice, this wouldn't work at all, and this is because the world supply of xenon is actually only 40 tons, and in this design we're using 940 tons of xenon. And by the way, this would cost $3 billion in today's market, but of course we're not able to produce anywhere near that level of xenon, and so we would need to use argon or a different gas that's more common. However, designs that use argon usually have a lower specific impulse, which then means we need to have more mass dedicated to propellant, and that means less mass that you can put towards solar panels and payload and tanks and everything else. So can we theoretically make this? Yes, but should we make it? I'll let you decide, and I'll give you my opinion as well, which is no. Okay, so my main conclusion is that we shouldn't make this kind of reusable electric platform, at least in these early stages of the exploration and the settlement of Mars. And this is my basic philosophy, that we should almost never bring anything back to Earth from Mars or the asteroid belt, or really anywhere. And that's just because of the basic physics of the situation. So I made a whole other video that I'll put in the description talking about how difficult it would be to produce propellant on the Martian surface and then send back starships. And I'll just say it's almost impossible. It would take thousands of tons of equipment and would take something like 50 to 100 starships at least. But then you get into the thing where you have an opportunity cost. So you don't want to dedicate 100 of your first missions to Mars all towards just sending one mission back to Earth. Okay, that doesn't really make any sense. And so going to Mars and actually coming back is a massive luxury. Okay, we spent so much to actually send these people and equipment to Mars that it doesn't make any sense to just send them back afterwards when they can continue doing tons of useful work on the surface of Mars. And this is like the first pilgrims who came to America. They didn't want to just go there for a year and then come back and tell everyone about it. No, they wanted to go there and settle it and create a civilization in this new world. And so that's the whole point of going to Mars. But anyway, that's just my opinion, is that we should have a much more hardcore settler mindset about Mars and try to make the best potential of every kilogram of mass that we send there. Okay, so now let's compare this to a standard chemical rocket mission to Mars using something like Starship. So in this case, we only need around 15 kilometers per second, maybe slightly more. And so it's relatively easy when you compare it to that crazy reusable two-way mission. So in this case, we're using Starship, which has a 150-ton payload capacity, a 1,500-ton propellant capacity, and the upper stage has around 7,000 meters per second of delta V. And so if we have 10 orbital refilling flights, we can expect this to fully refuel Starship and give it 7,000 meters per second of delta V from low Earth orbit. And this could also improve over time with improved tanker designs, or just version 3 or version 4 Starship as well. So if it does take 15,000 meters per second, we can just subtract 15,000 minus 9,300, and we have 5,700 meters per second left over, which is how much delta V we need for our mission. Again, it would probably be slightly more than this, but let's just use this as an example. So in this case, the 7,000 meters per second from LEO would be sufficient as long as there's negligible boil off. We could also do a scenario where we can refill the Starship in a higher orbit, and this could give it 1 to 2,000 meters per second of additional delta V, and this would also probably take 10 to 50 additional Starship refilling flights, depending on how much delta V you want to add, and there's sort of diminishing returns to this. Now, again, if we compare that to our electric platform, that again only had a 500-ton payload capacity, so it could barely even take a partially fueled up Starship. This would also take 10 to 20 flights just to put it into orbit, and then you'd also need to somehow assemble this thing within orbit as well. Now, this would also take probably closer to 2 years one way, or a total of 4 years two way, versus the 6 months expected for the chemical mission. So this would take basically the same number of Starship flights for both of these missions. However, building the actual electric propulsion system would probably be close to $20 or $30 billion. This would be 10 megawatts. The International Space Station is only 200 kilowatts. Okay, so the scale of this thing is something like 10 times that of the International Space Station. And if we assume that Starship refilling flights can eventually become as cheap as a Falcon 9 mission, then we can expect the simple chemical mission to be closer to $2 or $3 billion if you don't include all of the Martian landing and Martian equipment. And that 20 billion number I gave is actually really generous because there's tons and tons of development that we would need to do in that process, and it would probably not happen for decades, especially with NASA's rate of progress. And so really the most practical decision for the medium term and the short term even is standard chemical rockets for getting to Mars. And one more point for the chemical mission, you could also use expendable starships, or you can use upgraded tankers that are much more efficient. And then, the design is constantly improving. So you can actually pull this off with probably less than 10 flights. And like I said, if they could pull off a mission where you don't actually need 7,000 meters per second from low Earth orbit, then you would need even fewer. So a fully chemical mission makes more sense than a fully electric propulsion mission. However, I wouldn't write off electric propulsion completely. Okay, so we can actually make these designs of a hybrid mission where we use both of these technologies and try to make the most efficient design overall. Okay, so my first idea is called Hybrid Mission 1. And the idea here is that you would do what is normally done in a refueling type situation where you can have something like 10 starships go up in low Earth orbit and fully refuel a propellant depot. And then you can have an electric propulsion system attached to this, and then you'd only need to give it maybe 2,000 to 3,000 kilometers per second to lift it into a geostationary orbit, which is a much higher energy orbit. Then you could have a mission of Starship that goes all the way out to geo, and this would probably take refueling on its own. But then you would fully refuel it at that point, so it would have 7,000 meters per second up there where it's already out of the gravitational influence of Earth. And then, so to get into that Mars injection orbit, instead of taking 3,000 meters per second, it would probably only take 1,000 meters per second, or maybe 1,500 meters per second. Okay, but if you really think about how complicated and expensive this would be, it almost certainly would not be cheaper than a chemical mission, but it is cool to think about. Okay, now the second hybrid mission that I considered is actually using nuclear electric propulsion like what was originally proposed. And the idea here is that it's for a very deep space mission. And so these would take, these usually take 5 to 10 years when you're going out to the outer planets. And so in this case, you would just have a normal chemical rocket mission, and then just attached to your spacecraft, you have a nuclear electric booster. And in fact, they already kind of do this in several different missions, so this isn't really a novel idea at all, but this is just a use case that makes much more sense. And now, since you're doing it over a time scale of like 5+ years, this requires much lower thrust, and so it's going to require much lower cost for solar panels or nuclear, and also much lower cost for the thruster itself. And so this is basically why it's actually used in this sort of situation. And so I do kind of imagine this as being useful for those missions after Mars when we're trying to colonize the asteroid belt, and when we want to get a lot of mass out there very efficiently to start having these von Neumann probe type settlements. By the way, I have another video of colonizing the asteroid belt that I'll also leave down in the description if you're curious. Okay, now one more thing I was thinking about is Elon Musk. He's always saying that he needs 1 million tons to the surface of Mars to make it a self-sustaining civilization. And I was thinking if some sort of reusable platform would make sense for this sort of long-term goal. Initially, you would think it would make sense because it could be much more efficient. You can make it round trip, so it could be reused. However, the problem is you still need around the same amount of flights because you need to actually refill the propellant in these things. Since they still have roughly 50% mass fraction, it can't do multiple flights without being refilled. It's also sort of unlikely that it'll last longer than 30 or so years, like just most spacecraft in general. And so in the grand scheme of things, I would expect this to be much, much more expensive than just expending something like Starship, expending spacecraft that are sent to Mars to land and stay there. By the way, if we get to the point where we've sent 1 million tons to the surface of Mars, they're going to have plenty of equipment to the point where astronauts are not going to need to ever come back to Earth, like they did in The Martian, for example. So in conclusion, I think electrical propulsion and even nuclear electric propulsion can be very useful, and I think we should continue developing and improving them, but it's definitely not a silver bullet that can replace chemical propulsion, especially for getting to Mars. And it's definitely not going to replace the function of SLS. And speaking of SLS, I do agree with Jared Isaacman that we should be canceling this program and moving to some more reusable and sustainable chemical propulsion type platforms. And I really liked his article about the problems with NASA, so I'll leave that down in the description as well. And it was really disappointing to see that his nomination got canceled to be NASA administrator because Now they're not going to have an official administrator for something like a year. And this was because of Elon Musk leaving the Trump administration. And they ended up sort of canceling Jared Isaacman as sort of a punishment for him, which was sort of unfortunate. So NASA is definitely going through a lot of struggles, but I think regardless of who the administrator is, NASA is not going to really be doing any major human spaceflight advancements within the next 10 to 15 years. Okay, this is really going to come down to commercial providers, especially SpaceX and Starship. Hopefully that program, they can work out the kinks and we can see some landings on Mars put it in the next 10 years. I think that would be really incredible. But we'll just have to see. Anyways, let me know what you guys think down below. I always like reading those comments. And with that being said, make sure to like, subscribe, and share, and have a great day.